subscribe. There you go. You click there, and then you get access to all these videos. Okay, but we're not going to talk about that. We're going to talk about dust. A topic that's not too unfamiliar to most of us who live in the desert or visit deserts. Today's going to be a talk about a desert at the bottom of the world, which is actually the driest desert, far drier than we are here, and it's called Antarctica. And then I'm going to talk to you about another desert that I go to called the Atacama Desert of northern Chile, where I spend my time nowadays. But all of this comes down to battling the bane of my existence, which is called dust. Dust is the villain of my memoirs. As Mike was saying, it's really a memoir. It's not really a dry technical science book. A memoir, what it feels like to try to do science against all odds, including those man-made idols and odds called the Nobel Prize. But even that's a relatively small fraction of the book. Mostly it's about wanting to uncover how did it all begin, the title of today's talk. And I always say that when I was a kid, you know, you read a book and it has these dust jackets, right? And you're reading about like the dust jackets like falling all over the place. And I hated dust jackets. And I was like, who the heck needs it? Like, how much dust is raining down on libraries everywhere? But it turns out, I'm kind of a rare book aficionado too. It turns out if you have a book and it's of any value and you don't have the cover, the book is worth 10% of what it's worth with the book jacket. So these dust jackets are incredibly important for publishers, for authors, and yet, you know, to me they fall on the ground, they kind of make a mess. But I've come to love them in a certain sense because I realize in a way that in order to get to the meat of a book, you need to get past the dust jacket. And the dust jacket of the universe is really in our cosmic backyard. It's the dust that obscures or attempts to obscure our view to the deeper cosmos beyond. And so it will play the role of sort of a villain. Yes?
So people who are watching are not seeing your screen.
They're not.
They're not seeing it, so yeah, you can get shared if you're not.
Share screen.
We always have stuff like this, right?
They could hear it.
Huh?
They could hear it.
They can hear him? No, they
I'm
can.
asking, could they hear him?
I don't think so, but I didn't ask that, but I just thought it wasn't showing up. Let's see, so you got a screen share there?
Oh yeah, that's kind of hard to see, isn't it? All right, let me move over here. But the problem is...
There it is.
There you go.
There you go. It's
Okay.
second from the left on the right, it looks like.
This one?
Yeah.
Yeah,
It's going to be this one. Let's see.
yeah.
Okay.
You can do this like 1,000 times, and you always have this. Always. Let me see.
Okay, can
you
you-
think you are now?
It's showing I'm sharing this screen. That's the problem. You're probably seeing my two
Okay, you're
screens.
good.
Okay.
Yes, you're good.
Okay, good. So we're going to talk about stuff that happened starting billions of years ago. But before that, we're going to talk about things that happened hundreds of years ago. And I said I'm really infatuated with old books. That's me holding a copy of one of the most famous books in history, certainly in science history, but maybe in all of history. And it's called the Sidereus Nuncius. And it was published on the most important day of the year to me and at least one other person in this room, March 13th, 1610. It was published on that day. So somebody here knows that date. Very important date. And what it is a first kind of popular science book. It's an illustration of what Galileo saw through this tube that he called the perspective tube. And we call it a telescope today. So you guys are not following my advice to stay awake by being... No, just kidding. No, everyone's staying awake. Thank you very much. So Galileo didn't invent the telescope. It was invented by a Dutchman by the name of Hans Lippershey. But he perfected it. He took it from, like, say, a 1 to a 10. And when you do something like that, you can really get a monopoly on all sorts of discoveries. I say it's like, you know, you discover that, you know, you get static electricity when you rub your hair on a balloon, somebody shows you that, and then the next day you go and build the Large Hadron Collider. It was such an incredible order of magnitude over anything that had been existence before that he then proceeded to make like hundreds of discoveries that no one had ever thought to do. Even though the telescope existed, it's amazing to me. Nobody ever went like this. Oh, let me see what that white thing is up in the sky tonight. But Galileo did it with the telescope. And then he improved it, amplified it, made it better. So what did he see? Well, he saw these circles and stars. And, you know, today with, like, you know, the metaverse and 3D graphics. It doesn't look really good. But that is an amazing image in the upper left. It shows the planet Jupiter surrounded by these little stars. He called them stars, Galileo. And he tracked them from January 10th to January 13th. This is all in 1610. Then in March 13th, he published it. It's only 2 months between observation and then self-publication without peer review, which will come back to haunt him later. And then he shows that thing that looks like an H. That's Saturn, as he perceived it. He said Saturn is threefold, meaning that he thought it was actually 3 separate bodies. But the other image below is the planet Venus, which to your eye just looks like a dot, very bright. But he saw it looks like a little miniature moon, meaning it must be inward of the Earth towards the sun. Just like the moon sometimes is inward of the Earth to the sun. But the upper left image is really spectacular, because with that image, I would have stopped after the second day. I would have been like, all right, there are these stars, and it's near the planet Jupiter, but it's just moon. But he kept following it, and he realized what he was looking at was like a miniature solar system, viewed edge on. In other words, he realized instantly those dots were moons orbiting the planet the same way our moon orbits it, and that it had form. Like, you can't imagine the conceptual leap that it took to visualize there could be more than one moon around a planet. How many people have seen out here, you must have, seen Saturn or Jupiter through a telescope? So when you do that, you're seeing like 5, 10 times more moons than any other normal person has ever seen. But most people, he was the first person to ever see it. So the first to do something is quite amazing. But I say it's really important, this discovery, and it's the most important scientific discovery ever done, in one way because the scientific discovery is one thing, but with a telescope, you can repeat how it felt for him to do it. In other words, he didn't just observe it passively. He was moved emotionally, and you could be moved emotionally in the exact same way as him. Just take a telescope out, or better yet, get one for a kid. So tonight I have on sale Keating brand telescopes for $19.95. No, I don't. I need to do that. My kids need to go to college. UCSD tuition's going up. And what he would do is he would sketch the way it felt to see these things. Not only to see the thing, but to sketch the way his visceral impression was. And to me, that's just phenomenal that he could communicate. Right? He was an artist, he was a poet, and he was one of the master scientists of all time. And I'm pleased, this is a parenthetical, to be involved with him in just a small way. But as Tom and I know, being faculty members, you know, the most important thing for a faculty member, what is it, Tom? Publications, also tenure, and startup. And so he wanted to get, he was kind of working for hire as a math tutor, which wasn't really considered that high praise. And he really wanted to make a lot more money. And he realized, just like today, the way to great riches is to go and have some military application for your technology. So there he is in the tower in the Piazza di San Marco in Venice. And he's showing the Senate and the Doge. He's showing them that with this telescope, you can see an enemy Roman ship 3 days before you could see it with your naked eye if you have this telescope. So it was like, we have this B-2 stealth bomber, but like with a piece of glass, you can make it visible from any, I mean, it's incredibly valuable. And he sold it, and they immediately gave him tenure and doubled his startup funding in Padua, I believe he was. And it was quite incredible, but Galileo had many illegitimate children and mistresses. He was somewhat of a playboy, scientist playboy. You can imagine such a thing. So even this doubling of his salary, that wasn't enough. That's right. That wasn't enough for him. And so he decided he would do what Tom and I often do, which is to go on a book tour. So he went on a book tour. And like this entrepreneurial fellow, woman. So he actually became instantaneously famous all over Europe. He never left Italy, but his fame spread such that even Shakespeare wrote about him, and all the way in England, almost instantaneously, with some characters based on this wise, noble, natural philosopher that was obviously Galileo, and they were contemporaries. So he went on a book tour, and he said, this is a pretty good life, you know? I don't have to do Zoom classes. I can just write and do my authorship, which he really loved. He made a lot of money. And so he took it a little bit farther than he should. So he ended up writing this book. This is called the Dialogo. Now, Sidereus Nuncius, I know for this erudite audience, you all speak Latin. Sidereus Nuncius in Latin means the starry messenger in English. The Dialogo is Italian. In other words, he was forbidden by the Pope to teach the Copernican theory, which I'll explain in just a second. And teaching meant communicating in the vernacular of the time and of the place, meaning that he couldn't speak, he could research it, he could publish in scholarly journals that nobody read, but he couldn't teach it using the common language, namely Italian. But he somehow forgot about that and thought that because he got so close to the Grand Duke of Tuscany, that the Pope, was the head of the most powerful military, that he would somehow forgive it. But of course he didn't. And what happened next wasn't so great, but I'll explain that in just a second. I think it's funny because in this book, the Dialogo, it's called The Dialogue on the Two World Systems, which means is the universe Copernican? Is the sun the center of the universe? Or is the earth the center of the universe, as the church and Aristotle had maintained? But he puts in his title, Linceo. Linceo means the lynx. That was like the Nobel Prize of its age. It's called the Academy of the Lynxes. There's actually a Linnaean society in San Diego I've spoken at. And this was published in 1632. And one of my proudest accomplishments is that one of my friends in San Diego happens to know, so I'll take a step back. I was doing a video about the dialogue, and I didn't want to read it because it's 500 pages. I felt, it's kind of going to be stilted language. It's translated. Let me get the audiobook. How many of us listen to audiobooks? I do it all the time. I've listened to over 100 audiobooks in the last 2 years, or read some books every now and then. But I was like, let me get the audiobook. Doesn't exist until now. So I was able, through some connections, and the University of California owning the translation, to get the rights to make the first ever audiobook of the dialogue. It's coming out next month. And I did it with a very famous physicist named Carlo Rovelli, who wrote a book called 7 Brief Lessons on Physics. Very famous scientist, a couple of Nobel Prize winners. And it's really kind of a labor of love. It's 24 hours long. And it's a trialogue between these three characters explaining that this system on the left that was maintained by the church is kind of ridiculous and should not be believed, even though the Pope maintained it was true. And the system on the right is, of course, Galileo's favorite system. And that really wasn't proven until 200 years after the authorship of this book. And that's another story for another day that you'll find out if you do subscribe to my podcast. I'm going to have the authors, the other co-authors of the book, on to discuss what went wrong with Galileo, how his hubris eventually led him to making a great mistake. And so this is Galileo, a famous painting from the 1800s. It's called Galileo Before the Holy Office. The Holy Office is a euphemism for the Inquisition. It's like, the IRS, the money donating service, right? It's a euphemism. So you see Galileo in the middle, and he's like elderly, and this is after the publication of the dialogue that he was forbidden to teach using Italian, and so there's a conquistador-looking guy there. And so he was imprisoned. He wasn't actually tortured. He wasn't, almost executed, but he was threatened with being tortured. He was threatened with being executed. So that's almost quite as bad. So, and there's the Pope, who had been one of his tutors, mentees, so to speak, that he had tutored decades earlier. So he miscalculated that he could get away with so much because of his brilliance. Now, I like to lay to rest the myth that he was tortured. This is his prison, quote unquote. This is a place that only, Jussie Smollett could only dream about going to such a prison. It's got olive trees, it's got a vineyard, you can see the Duomo, it's unbelievable. And this is where I had a conference that I hosted at his house, at his final villa, where he wrote the final book of his life called The Discourse, which I hope to put out some years from now, as well in audiobook form. But it's not exactly that he was tortured. So let's skip ahead a couple hundred years. And we see that telescope technology has come quite a long way. We have images such as this one from the Hubble Deep Field, which you can't really see with a small telescope like Galileo had. But every single image in this picture, except for this one, every single image is a galaxy. Not a star, a galaxy. That thing with the cross on it, that's a star in the Milky Way. Everything else is a galaxy like the Milky Way. And you might think, well, this looks pretty big. How many galaxies are there? So if you just add up how many galaxies are in this picture, 5,000 or so galaxies, then you ask, how big is that image on the sky in reality? It's much smaller than the size of the full moon. And you can calculate how many galaxies are there in the observable universe. And you get about 100 billion, where each one has about 100 billion stars in it. So you have 100 billion stars, squared number of possible stars in our observable universe. And some people say, as we'll get to, our universe is not the only universe. And that's an extension of the Copernican principle. We're not the only planet. Our sun is not the only star. Our galaxy is not the only galaxy. Why not the universe not be the entirety of all universes that could exist? Now, in 1965, in of all places, New Jersey, I hate to say it as a New Yorker, but New Jersey, they discovered radio astronomers using a telescope that doesn't look like a telescope. It looks like a giant funnel or gramophone, but it's really kind of like a gramophone for microwaves and radio waves. And they observed this constant, persistent hiss of glowing radio waves in all directions, which they properly surmised with help from my PhD advisor's PhD advisor, my grand advisor, David Wilkinson, and others, was the afterglow of the formation of all elements on the left-hand upper side of the periodic table. Namely, what they had spotted was the glow that emanates from the Big Bang. And this was the first physical evidence and best physical evidence that there was a Big Bang. So this was discovered in 1965, and they won this golden medallion. And then over decades, my colleagues and some work that I've done has led to even more refined images. This is from NASA. That shows the entire sky as you'd see it if you had microwave-sensitive eyes. And the question is, how do those little fluctuations, which were really, they're going to instantiate those galaxies. They're going to provide the nucleation, the seeds for these galaxies to form. Those are the imprints in this image of microwaves. To go through it in great detail would take a book that's available for $15.99. But suffice it to say that what we want to know is how did these fluctuations, the seeds, get there in the first place? It's like a chicken or egg type problem. One of my kids said, it's easy to find out which came first, the chicken or the egg. Go to Amazon, order a chicken and egg, see which comes first. You can guess which one of the kids. So these fluctuations must have been seeded by something. Cosmologists have a very good idea and conjecture that what did provide the seeds was an earlier epoch prior to the Big Bang, and that the Big Bang wasn't really time equals zero. There was some pre-existing substance, in this case called a quantum field, called the inflaton field. And it has these fluctuations. And these fluctuations lead to the impression that you later see on top when the universe is a few 100,000 years old. So I'm going to have a mint, because my throat is dry out here in the desert. So our image of the universe goes beyond what Galileo saw. It goes beyond Jupiter, goes beyond clusters of stars, beyond galaxies, beyond even the Hubble Deep Field, all the way out to this epoch that's called the cosmic microwave background. And that's what I study. And the question is, did something come earlier than that? I always say, I want to know what happened on the Tuesday before the Big Bang. Was there another universe? Did our universe start from nothing? Did it have a beginning? And if so, if time began, how can time progress if time begins? How can time actually, which measures the change between something and something else, how can that change when there was initially no such thing as time? Not only did time progress, time came into existence. To me, it's one of the most fascinating things you could study. And myself, my colleagues, and I asked this question: how could you measure what came before the formation of that heat pattern or the formation of the first elements? And whether or not you could prove that the universe underwent this inflation expansion faster than the speed of light, kind of the spark that ignited the Big Bang. So we know the Big Bang happened. We know there's structures in the universe. Where did those structures come from? Who planted the seeds for those? So, with help of colleagues, we realized there'd be a distinct pattern. There'll be unequivocal evidence for this epoch of inflation. And that epoch, that signature, is called this swirling, twisting pattern of microwaves called B-mode polarization. I explain it, as I said, in the book. But suffice it to say, it's not unrelated to something everybody out here has, which are polarized sunglasses, right? Everyone hopefully is wearing their polarized sunglasses, not at night. So polarization is a tendency for light to to be oriented along a particular direction. Light has different properties, one of which is how does the light wave oscillate through space as it travels. So a polarized sunglasses, what they do is they filter out all but one state of oscillation. So this is a piece of Polaroid, and these screens are usually very highly polarized. And you can see as I rotate it, every single time I rotate it once, the brightness and darkness goes through 2 cycles. Watch this. So I'm starting, it's completely dark. I rotate 90 degrees, completely light. Now it's 180 degrees, completely dark. That's only half a rotation. Now it's completely light again. And then it goes back to dark. That's unique to polarization of light. The only light will that happen for. That's polarized. So we had to build a polarization sensitive telescope. Well, how do you do that? You take an ordinary telescope and you put one of these in front of it. That's literally what you do. Except we're detecting not light waves, but radio or microwaves. So we use separate kinds of detectors that I brought a version of here. And it doesn't look like any kind of detectors that you've ever seen before because they're made out of what's called a superconducting quantum interference device. So the details of that are a little bit more complicated. But suffice it to say, we built a similar type of telescope conceptually to Galileo. We built a refracting telescope that uses lenses, not mirrors. And at the focus, we don't have our billions of pixels in our eye, but we do have hundreds of pixels that can be cooled down almost to absolute zero, 0.25 Kelvin, colder than it was here this morning in the desert. And instead of glass lenses like this guy has, we have to use microwave transparent. This glass is opaque to microwaves. But that glass, which is made of high-density polyethylene, is very much transparent and refracts the microwaves that come from the Big Bang. We put that in a telescope on a platform instead of holding it with our hands. It's about 10 feet high. It acquired a Twitter account, thanks to me. And we had to put it somewhere. Instead of moving to northern Italy, we took it to the bottom of the world. Now, this is an image that the magazine Nature made after when my book was published, and they did a review of it. They trashed it. No, it was a nice review, actually. I'm very happy with it. And they made this beautiful image. It shows radio astronomers staring up at the sky looking for the Nobel Prize. And why is that? For a long time, people said it's a guaranteed Nobel Prize. If we discovered the signal that I set out to measure 20 years ago, it was guaranteed to be a Nobel Prize. Why? Because not only was it measuring these microwaves from the Big Bang, which had already been a Nobel Prize, not only would it have been the discovery of this inflationary quantum field, but it would also be a representation of what's called quantum gravity, and also be a discovery of this philosophical paradigm called the multiverse, which would be effectively to the universe, which means one universe, one cosmos. It would be as expansive as the notion of Copernicanism, that the Earth is just one planet and the sun is just one star. Some would call it, and did call it, the greatest discovery ever made. But of course, spoiler alert, it's called losing the Nobel Prize. So something must have gone wrong, right? So we took it, this is our first desert. We took it to a desert. Now, most people don't think Antarctica is a desert, but it is. It's actually the driest, highest, windiest continent of all 7 continents. We took it smack dab to the middle of the continent, which had been only discovered about 100 years ago. So it was the last most remote place on Earth, only reached in the 20th century. It's kind of amazing. People didn't even know the continent existed. They conjectured the existence of the continent based on the following logic. They recognized in the 1500s the Earth was a sphere. They knew that the northern hemisphere had a lot more ice and icebergs, and they conjectured there must be an equal amount of icebergs in the southern hemisphere so that the Earth doesn't flip over. Okay, that was like the theoretical basis for the existence of Antarctica, which wasn't discovered itself. The whole continent wasn't discovered until the 1700s. It's kind of amazing. We go to the South Pole. Here are the first 2 teams to get there. There's a team at the top that was led by Roald Amundsen, who's a Norwegian explorer, who tried and failed to get to the North Pole for the first time. He immediately turned around after he lost the Nobel Prize of its time, lost the North Pole, and he took a sled team led by dogs from New Zealand and eventually got to the coast of Antarctica and skied 700 nautical miles from the coast of Antarctica up 9,000 feet of glaciers to polar plateau in wind and very desperate conditions. And the British team, led by Robert Falcon Scott, I love that name, his team refused to take dogs because every animal that had ever been brought to Antarctica was used as food at one point. And the Norwegians didn't mind having, après-ski and eating dog for their après-ski, but the British refused to do it. So they chose to pull it themselves, which meant they had to take even more food for themselves to eat because they couldn't eat the dog meat. And also they burned more calories. They burned 10,000 calories a day, each man. They got to the South Pole 3 weeks after those guys, and they all died. Because by the time, actually, in March, they froze to death on the way back. So a difference of 3 weeks and thousands of calories meant the difference between life and death for those folks. Nowadays, it's still incredibly dangerous, as this video I shot on my last visit down. I've been there twice, but they have these wonderful penguins, and people say, oh, they're so cute, like the ram, like don't get too close to the sheep, right? Don't get too close to the penguin. They look nice. They're a nasty bird. They're a nasty bird. So you go there and you want to prove that you made it. You send your wife a picture and put it on Instagram. And then we actually discovered that pattern that I said is the imprimatur of inflation. We claimed that we detected this pattern, which would imply the existence of this inflationary universe, which would imply the heat that expanded the universe and the creation of all the elements. And by the way, that's not all. You also get a multiverse. So it was one of the biggest discoveries at the time of all time. That was 2014, 8 years ago, next week, St. Patrick's Day, 2014. And it resulted in press conferences. It resulted in viral videos from Stanford University, 3 million views for a science discovery. It was incredible. Champagne toast, that's one of the discoverers of the prediction of inflation. Andre Linde, who's
Stanford University.
Former Soviet Union physicist who moved to Stanford.
Today I'm going to deliver a news to Professor Andre Linde, who is the founding father of inflation. So inflation is the theory about the bang of Big Bang. It explains why we have all this
Andre
stuff
Linde to win a
in the
Nobel
universe.
Prize.
So
I won't
today
go through the
I'm
whole
gonna tell
thing. It's
him
kind of
our
a little bit
experiment by
cringeworthy
Statue
nowadays to
South
watch it.
Pole has found the smoking gun
There's a couple guys in
evidence
this is
of
John
inflation.
Mather.
He has no idea that I'm coming.
Pin there. So this is quite amazing. It was on CNN. It was on the front page of the newspaper of record, the San Diego Union Tribune. And there I am, gazing up at the heavens. There it is on the New York Times. Space ripples seen as Big Bang's smoking gun. I like the bottom print from The Economist, which says, like some guy suddenly sees the Big Bang. Amazing. Like I'm just watching. Oh my God, the Big Bang. Amazing. Now we knew from the beginning that it's possible in science to see things that aren't really what you think you set out to see. In other words, that there could have been a signal mimicking what we were looking for. In this case, cosmic interstellar dust. And in fact, there's this beautiful cartoon of these, house cleaners or whatever. And they say, sure, it's beautiful, but I can't help thinking about all that interstellar dust out there. And it was kind of ominous and prescient because within about 6 months, we went from surefire Nobel Prizes for all, biggest discovery of all time in science history, to retracting the discovery. And what's so interesting is that we tried to study the biggest thing there is, literally, the universe. And we were kind of humbled by the most humble substance in the universe, which is this cosmic schmutz that we couldn't get away from. And what is this schmutz? Well, it's nothing other than these things that you've probably seen flashing through the night on August evenings. These are meteorites collected the old-fashioned way on eBay. And one of each will be yours if you buy a book. Each book comes with a free meteorite. So meteorites are the shrapnel of exploded stars. An exploded star that went off in our galaxy maybe 5 billion years ago. Its material circulated in zero gravity, eventually coalescing and forming the planets. And some of the material that is formed during a supernova explosion are these heavy metallic elements. And this is leftover ejecta from the formation of our solar system. Yours for only $10. And you can tell that they have certain properties, one of which is that they're highly magnetic. So in the Milky Way's magnetic field, these little grains of dust, smaller even than these meteorite chunks, can get aligned and exactly produce that swirling pattern of microwaves that I said is indicative of inflation. So it's an imposter signal. And that imposter signal effectively is what we ended up not retracting, but restating what we saw. So it's called a disconfirmation, when you fail to reproduce the signal that you saw. Now, it was produced on the front page of the New York Times and the Union Tribune. The retraction, so to speak, didn't come for months, and it was on like B17, the Saturday edition, which nobody reads. But we came to see the cosmos. The results aren't wrong. They're accurate and precisely measured, but the interpretation is not as we originally claimed. So the game is still afoot. Now we know the universe isn't like this, after all, where you have this pristine view from the Earth all the way back to the Big Bang, but it's more like this. It's more like downtown Los Angeles, full of smog and schmutz, and we have to look through it. And in a way, it's not so bad, because this dust is kind of, there's a book by Christian Deneuve called Vital Dust. And it's really a statement that dust is all around us. It's bad for scientists looking for the Big Bang, but without it, we wouldn't exist. Because that very material is, as Carl Sagan said, our entire planet, in a sense. He called it very famously. This famous image is called the pale blue dot. It's from the Voyager 1 spacecraft taken on Valentine's Day, 1990. He commanded it to point back to the Earth, and it just so happened that there was a sort of a light artifact of a sunbeam, like you've probably seen here. And that little dot at the center of that blue circle, he said, that's a pale blue dot. You see a dot. That's here, that's home, that's us. Every saint and sinner in the history of our species lived there on a mote of dust, suspended in a sunbeam. So it's pretty poetic. I like this from one of Sarah's friends. This shows 3 different types of dust. It shows the rocky earth, the desert, those little spires in Arizona. It shows the Milky Way galaxy filled with dust, cosmic dust, other solar systems, other beings perhaps. And then it shows 2 beings in the foreground. And the iron in their blood traces back to that same supernova that produced that same dust that caused this to blow away in the wind. Hemoglobin contains iron. That iron came from the same supernova. Your mother ingested it and produced the blood that's in your body. And your body takes over from there. So dust creates and dust destroys. So it pays to pay attention to dust. Now, how does this relate to the Nobel Prize? Well, I did say, if we were successful and didn't have to disconfirm our results, then we would have won a Nobel Prize. I'm still confident of that. What is the Nobel Prize? Well, it's the most famous and august award that human beings have. It's more powerful than the Latin Grammys, even. And it was created by Alfred Nobel, who died without any children or a wife, who called himself a misanthrope but excessively benevolent. And it was started because he read a headline while he was in Paris one day, and it said the following: Merchant of Death, Alfred Nobel is dead. Why was he the Merchant of Death? Because his family was an arms dealership. He dealt arms to the Russians, to the Norwegians, to the Swedes, and he was famous for inventing dynamite. He invented 355 patents, one of which was dynamite, and it led to thousands and thousands of people, perhaps millions, being killed. And it's kind of like anything. Like nuclear energy can create power, but it can also destroy our whole planet. So you have to be careful and have the wisdom to know how to use the scientific knowledge that scientists, human beings, after all, create. He endowed the will. He died the year after he endowed his will. It's pretty amazing. It has these 2 sides to it. And in my podcast career in the last 2 years, I've interviewed 11 Nobel Prize winners, trying to extract from them their wisdom, not their knowledge. Because I think knowledge you can get better than any Nobel Prize winner is something called Wikipedia. It has more knowledge than any human being could ever have. but wisdom is excessively rare, and I think much more valuable. So that was my goal in my second book, Into the Impossible. Available. Oh, no, I'm just kidding. Now, soon after the retraction, so to speak, I came to my office and I found this letter. And it said, Professor Brian Keating, we want you to nominate the winners of the Nobel Prize that you could have won if you weren't such a schlub. So imagine, like, Mike, you asked me, like, can you speak here? And I said, can I speak at the Art Institute instead, please? This is, all right, I guess I'll speak. So it was kind of humiliating, embarrassing. But I went through a little bit of a scholarly undertaking. I looked at his original will, went back to primary source materials, right? That's what you're supposed to do. There's his will. I speak fluent Swedish, so no, I don't. But in it says, the whole of my estate, so he had no kids, no wife, nothing, right? He gave all of his money, and he was like the Steve Jobs, Elon Musk of his age, incredibly rich. The prizes shall be given to those people who during the preceding year shall have conferred the greatest benefit to mankind. A portion is followed, one part to the person. So it's a single person who made the discovery last year and conferred by this discovery the greatest benefit to mankind. Now I want to give you a quiz. Also, that's a good way to keep people awake. Give them a quiz. Here are 3 different inventions or discoveries. And I want to ask you guys, they're all eligible to win the Nobel Prize. One of which even is the periodic table, who has, as you all know, I'm sure. Let's see if this works. So element, I said, I can't see it on the screen, but element 102, Tom, what is that? Symbol NO, what do you think that stands for? Nobelium. So there's an element named after Alfred Nobel on this periodic table, invented by Mendeleev, eligible for the Nobel Prize. Which one of these 3 things won the Nobel Prize? Raise your hand if you think number 1, the discovery of RNA, won the Nobel Prize. Okay, raise your hand if you think the periodic table featuring element 102 won the Nobel Prize. These are one of the most important discoveries in human history. Raise your hand if you think number 3, this lighthouse, won the Nobel Prize. And raise your hand if you don't like raising your hand in public. Of course, it's number 3. We all navigated here using lighthouses and buoys. Now, he won it, Gustave Deleuze, 1912. He won it before Albert Einstein won it. Albert Einstein discovered the theory of relativity in 1905 and didn't win the Nobel Prize until 1922. Gustave Deleuze won it for these lighthouses. It's incredible. And partially that was because Einstein was Jewish. And most of the Nobel Prize winners were Aryan or from Austria or Germany. And there's a little known rule that once you've won a Nobel Prize, for the rest of your life, you can nominate Nobel Prize winners. And your vote carries this excess weight because you can always do it for the rest of your life. So these Germans, in fact, one of the Germans, his name was Philip Lenard, and he was the head of what was called of Hitler's Aryan science program. And Einstein was a Jew, obviously not an Aryan, but more than that, he was doing theoretical physics. This mumbo jumbo with equations and speed of light. He wasn't doing proper Aryan German science, which is experimental physics. Kind of ironic, since I'm Jewish and I do experimental science. So they would have maybe found me slightly more tolerant. There are some controversial Nobel Prize winners presented without comment. Some nominees you might be familiar with, the guy on the left. Woman on the right represents a sex scandal that shook the literature prize. There's even a San Diego connection, something very controversial. William Shockley, who's a professor at Stanford, or he's a co-inventor of the transistor, he donated some of his genetic material to what was called the Repository of Germinal Choice, better known as the Nobel Prize Sperm Bank, located in beautiful Escondido, California. I don't know if anyone made a withdrawal from that particular bank, but he wanted to rid America of the Negro, the contamination of the Negro species. It was a completely contemptible human being, and yet he was celebrated, and they actually basically based this site around him. So it's incredible that such things still happen, and even today there's calls to take away Nobel Prize, but no Nobel Prize has ever been rescinded. Harvey Weinstein can get his Academy Award membership retracted, but they'll never retract a Nobel Prize. It's kind of strange. I'm going to skip over this. Until recently, only 2 women had won the Nobel Prize in physics, including UC San Diego's own Maria Gephardt-Mayer. Then when she won it, her son told me this story, and I looked it up. Look at the headline in 1963. San Diego mother wins Nobel Prize. And we all laughed because that wouldn't happen today. 4 years ago, my friend Frances Arnold, she won the Nobel Prize in chemistry. She's at Caltech. And this is the headline in the Jet Propulsion Laboratories newspaper. Caltech mom wins Nobel Prize. Son is JPL Mars flight technician. So that was all before 2018. Thank God my book was published in 2018. And because of my book, and no other reason, the number of women winners has doubled. Thank you. Thank you very much. That's all. No. It has nothing to do with me. Fun fact, I've tried to get both of these brilliant women on my podcast. But unlike my wife, they reject me. And, and I have not been able, but I'm going to keep trying. I want them very much to come on the podcast. Last thing I'll say is about another Nobel wannabe, number one, a man by the name of Mahatma Gandhi. Nominated the same number of times as Adolf Hitler. True story. The seeker after truth should be humbler than the dust. The world crushes the dust under its feet. But the seeker after truth should so humble himself that even the dust could crush him. Only then, and not until then, will he have a glimpse of truth. And this is called his experiments with truth. I like that. So we got to work with the dust. We got to acknowledge the dust is there. This brings us to our second and final desert of the night. We are building the Simons Observatory in Chile. I am proud to be the director of this amazing group of 300 scientists from all over the world. My partner Suzanne Staggs at Princeton University is our spokesperson. Here's from our last meeting in July 2019, face-to-face meeting. Our next meeting, if you happen to be around and want to meet some fun, nerdy astrophysicists in July 2022, will be at UCSD. And can't wait to get together. It's funded by these two foundations, plus our partner institutions. And what is? Well, we know dust exists. We know the cosmic signal could exist. We have to get rid of the dust. How do we do it? Science isn't that complicated. People think you're an astrophysicist. I say, I'm not a brain surgeon. I'm just a rocket scientist. How do you guys get rid of dust? Vacuum cleaners. We're making the Simon Super Sucker. It's going to go into the galaxy. It's going to suck up. No. Wouldn't that be funny? No, we're building another type of telescope. The only way to get rid of an unwanted signal is to measure it and remove it from the data. We can't go out and build a super sucker. So instead, we're going to the Atacama Desert. It's in northern Chile. It's twice as high in elevation than the South Pole, 17,250 feet above sea level. These are all dormant, not inactive, but just dormant volcanoes. They could go off at any time. In fact, one did. The one that's on the far left is about 20,000 feet tall. There's the world's highest lake in the middle of it, Volcanic Lake. And so this is where we're building it. It consists of 4 telescopes. One is 4 times bigger than the Hubble Space Telescope. It has a reflecting design. The telescope sits in a building that's 45 feet high. And it rotates. The entire building spins around on its axis to look for these faint signals. Its detector system is that circular silver-looking thing at the top. And those are human beings next to it. We can fit pretty much every person in this room inside of the camera. Then we have these refracting telescopes like we used at the South Pole. And there's 3 of those, and they're much smaller. They're like human size. And they sit inside these big shields to protect us from wind and from dust and all sorts of things. We use very sensitive detectors that Suzanne and her group are building all around the world. And we can both measure dust and the CMB, the cosmic microwave background. Then from the combined signal, we can measure the dust-only signal, subtract it, and we're left with the pure cosmic signal, which may or may not contain the signal of inflation. So we just don't know. There it is in Chile, under construction. This is actually last year. We have to build everything ourselves. We have to bring concrete. We have to bring diesel fuel. We have to do this, and it's very cold, very intimidating place. It doesn't look like a desert, but it does snow here. It can snow in places like San Diego's high desert. So it can sometimes be very challenging. This is a little bit more recent picture from above. shows the different sites of the different telescopes. It should be taking data in less than 2 years. And so its goal is to measure not only the cosmic signals that could result in a prize like we've been talking about, but also measure the dust signals. So to be humble, taking the advice from Gandhi, and instead of only going after the glory signals, to also go after the signals that are unwanted, the foregrounds, the contaminations. So I hope if I've inspired you, you can perhaps get a copy of the book here or online. And if you get one here, as I said, happy to throw in a free meteorite and sign it for you. My other book, as I said, is a really distillation of the wisdom of 9 Nobel Prize winners that I've interviewed, and taking from them the lessons that we all have to deal with about collaboration, cooperation, creativity, imagination, synthesizing them in a way that appeals to not just scientists, but to anybody, no matter what you do. So I'm pretty proud of that. I have podcasts as well, as I've talked about, YouTube channel. I've already plugged that enough. Join my mailing list. Here's one last chance. Take a picture if you like, and join the YouTube channel if you feel so inclined. And I thank you very much. I'll take questions. Yes.
I have a question, but first I just wanted to point out that you'll get questions here and online.
Okay.
You pretty much need to repeat them so both audiences.
Okay.
But I also have a question.
Yes, Mike.
So as you're looking at these microwaves from the Big Bang, and the universe is full of dust, they shine a flashlight into a room basically that's got dust in it. Eventually that light will not get past that dust. I mean, it'll be intercepted and it'll basically wear out, right? I mean, you won't see it.
You mean from the CMB? So the question is the light that's being produced from the cosmic microwave background, or
the waves themselves, as they go through the universe, they're hitting obstacles basically as the dust. And so won't you lose track of them because they've been basically absorbed?
Yeah.
By all of this?
So Mike is asking a question. Just I should repeat it for people online. Yeah. So I was asking whether or not there will be enough sufficient absorption of these signals to preclude us from being able to detect the signals that we care about. The answer is no. There is a lot of dust, but there's not that much. In fact, water is actually worse for our detecting capabilities, not because it produces a pattern that could be mistaken for this inflationary signal, but because water absorbs microwaves. That's how a microwave oven works. It agitates by radio frequency stimulation. It agitates the molecules so much that they vibrate and they become so energetically excited that they start to boil. So we want to go to a desert or to space, but space is billions of dollars and we only have hundreds of millions of dollars. Poor us, right? But it's a huge challenge. So actually, if you take all the water in the Earth's atmosphere, even here, from here to space, it would be less than this bottle in height. So all the water molecules in the entire Earth's atmosphere wouldn't even fill up this bottle. And if you take a bottle width and extended it to space and condensed it, that's all it would be. It would actually be more like a couple of inches. So there's actually not as much as you think. So no, it won't absorb all the microwaves from the Big Bang. And we know that because we've seen the other pictures of the Big Bang that I showed you that looks like this colorful ball, so to speak. Yes.
The Alma Telescope in Chile
Yes.
is located at about 15,000 feet, specifically to avoid the water vapor.
Yeah, so someone's asking about the Alma Telescope. So the Alma Telescope is about 1,000 feet below us. So we're at 17,000, they're at about 16,000. And where you're standing, a couple of, maybe 100 feet more is where Alma is. We can see Alma from our observatory. So Alma is the most expensive observatory ever built. It's about €1 billion project on Earth. James Webb is 10, 15 times that. Yeah, that's right. Yes, in the back.
Well, in order to subtract the dust signal from the cosmic background signal, you have to have some way of measuring the dust signal without the cosmic background. How are you doing that?
Yeah, so you can never remove the signal from the noise, right? One way to think about it. The question is, how do you remove the dust signal? How do you measure the dust signal accurately enough in order to be able to subtract it? So dust is much hotter than the cosmic signal. The dust grains themselves are a balmy 30 degrees Kelvin, which doesn't sound that hot, but it actually is 10 times hotter than the CMB is, than the cosmic background that we're trying to see. The signal amplitude goes as the fourth power of the temperature. So it's 10 times higher temperature. That means it's 10,000 times more energetic So it's very easy to measure dust. You just have a channel that's at very high frequency. So we built in channels that can only see dust pretty much. And then from that, we compare it to the models of what dust would produce based on its physical characteristics, its temperature, and its orientation. And then we extrapolate to low frequencies and have good enough modeling accuracy that the uncertainties in the exact spectral shape and so forth don't really matter. And so we subtract out from the total signal. Yes, Tom.
You mentioned the James Webb Telescope.
Yes.
What is the difference between that that's been launched recently and what you guys are doing?
Yeah. So there's a question here as to what is the difference between the Webb telescope, which is the most expensive telescope ever made. It's about $15 billion just to launch it, and about twice or half that much more to observe for the next 20 years. So the James Webb Telescope is more similar to the Hubble telescope. It's an infrared telescope, which means it sees light of slightly longer wavelength than visible light that we can see. So like there are animals out here that can see and sense infrared radiation. It's at those wavelengths, twice to 10 times the wavelength of visible light, and it's not sensing polarization. It's looking for structures like galaxies, clusters of galaxies, but also exoplanets. It can actually resolve the atmospheric content of an exoplanet, a planet in another solar system, of which we know there are at least 10,000 in our local solar neighborhood, of which maybe several hundred are just like the Earth in terms of their proximity to their host sun, the type of sun that they're orbiting around. So that's designed to do completely different science at slightly higher redshift or earlier times than the Hubble telescope, but it's fundamentally similar to an optical telescope. In fact, there is a question from Jeffrey Love. The Hubble deep field picture you showed of galaxies of different colors. Why are they of different color? Very good question. So maybe I'll go back to that. Maybe that'll take too long. So they're different colors for different reasons. One is that they have different chemical compositions. They're different ages. And some of them have their own dust. Just like our Milky Way galaxy has dust in it, the galaxies at high redshift also have dust in it, because they're making stars like our galaxy has made stars. And I said the dust in our galaxy comes from an exploded star. You can't have a new star until the previous generation of stars blows up and produces the material to then seed the formation of new stars. And just like the sunset here is very red, right? But at noon, the sun is pretty yellow. So the sun changes from yellow to orange to red throughout the day, right? But it can't. The sun's not changing. It's just going through more of our atmosphere as it gets closer to the horizon. You go through more atmosphere, it goes through more dust. Dust scatters away the bluish, greenish, yellow light. So what's left is mainly red. So the more dust you look through, the more red and more polarized the sunlight would be. So that's part of the reason. Robert Televi is asking, is the source of galactic rotation angle originate ultimately in a B-mode curl rotation? I'll let Sarah take that. No, so no, they're fundamentally separate things. The question is about, is the polarization of the dust, does that relate to these B-mode, are they originating from a B-mode type rotation? The B-modes themselves, this twisting pattern, would only exist cosmologically if inflation occurred. So inflation doesn't affect our galaxy any more than, say, the Big Bang has a specific effect on where the Earth is relative to the sun. So no, it doesn't affect the dust polarization, but it can be mimicking the signal we're looking for from cosmology. Okay, no more questions online. Yeah, I'll take someone new and then I'll come back to you. Yeah.
Astronomers can't get the Nobel Prize, you know that.
That's totally not true.
No,
many astronomers have gotten the Nobel Prize.
A friend of mine, Jim Gunn, has gotten the equivalent of the
I know Jim Gunn personally, and he was awarded the Kyoto Prize in part by me. No, 5 to 7 astronomers have won it. Adam Rees won it, Brian Schmidt won it.
It's for physics.
I know that, but physics is now considered to subsume astronomy and even cosmology within it. So originally Hubble didn't win the Nobel Prize.
Yeah.
Jim could win the Nobel Prize. In fact, his colleague at Princeton is an astronomer, Jim Peebles. They're the same exact age. He won it 2 years ago. Astronomers discovered exoplanets. That's not physics, that's astronomy. They won the Nobel Prize in 2019. No, so thank God, you know, I can always lose it again. Hope springs eternal, to keep losing it. I said, you know, one of the worst things that could happen to my book sales would be if I win the Nobel. Behind you with the glasses.
Are you expecting to prove science now, or do you have an intuition of what you might find?
So the question is, do I have an intuition of what I might find? Certainly you design an experiment to have a specific capability to achieve a certain goal. You don't make some random, you know, discovery. Although a lot of discoveries in science do occur serendipitously, that's different. In fact, the scientists who did win the Nobel Prize, who were radio astronomers, in 1978 for the Penzias and Wilson, they were not looking to discover the cosmic background. They were looking for the first telecommunications satellites and found a persistent, irreducible amount of noise, hiss coming in all directions, static noise in their receiver that they couldn't get rid of no matter if they looked closer to New York City, away from New York City, at night, at day, during the winter, during the summer. They couldn't get rid of it. The interpretation was it was cosmic. So there is a danger, of course, in saying, I want to find this exactly and I'll stop at nothing. But there's also a practical matter that you have to know what you're looking for. When they built the Large Hadron Collider, it had a single goal. Unfortunately, that's all it's done, is detect the Higgs boson. It's a huge accomplishment, to be sure, but it really hasn't discovered serendipitous things the way that earlier discoveries made. Maybe that's natural because you picked the low-hanging fruit already with these decades of previous discoveries. So I like to think that there's some guaranteed science to be done. Even if the Big Bang didn't unfold via inflation, we'll still see things. We'll learn about dark matter and dark energy, things I didn't have time to talk about. But they're not quite as grand as discovering evidence for the multiverse, that's for sure. Yeah, in the back.
Would it be correct to think that you're looking out from the polar region in order that you're looking in a perpendicular direction to a cross-section of the Milky Way? So you eliminate a lot of the dust that you would see if you were looking through it.
That would be true if there was any relationship between the Milky Way galaxies pattern and the Earth. So the Earth has no knowledge of where it is in the Milky Way galaxy. So there's the Milky Way, which you've probably seen here, right? It looks like this band of milk. That has no relation to the Earth's equator necessarily. So therefore, it has no relation to the South Pole.
So they're not the same.
No. It would be convenient, but it turns out if you go to the South Pole and look straight up, that part of the sky is not super clean in terms of how much dust there is. That would have made it really convenient because then you could just look at one point for your whole life instead of spreading your time out looking over the whole sky. Was there one question? Yeah.
I don't understand how if you do what you want to, if you accomplish what you want, how does that provide evidence of the multiverse? I sort of miss that.
Yeah, no, that's a very good question. So the evidence that we would discover would be that there was, at the time preceding the formation of the elements, so the elements were born, if you like, if you go back in time from today, you go back 13.8 billion years, you know, plus a couple of million, you know, seconds or whatever, you come to a time when the last element formed in the beginning of the universe. Obviously, more elements are getting formed all the time. But the last element of, say, hydrogen was formed, or helium. Now, you ask, what age was the universe back then? It was about 20 minutes. So almost all the hydrogen in this bottle of water is 13.8 billion years old. It's pretty amazing. So when these hydrogens stop forming, now you ask, what happened before that? So the most you might think you could go back is 20 minutes. But, and that might be true. In other words, it might start exactly 20 minutes earlier than that. But it could be that the heat and energy that was used to form the hydrogen that's in here comes from what's called this quantum field. The quantum field will have existed. It had to exist before that 20-minute earlier period. So the question is, where did that come from? The only way that that can really fulfill the criterion that will later produce this and us and everything else is if it exists forever. So in other words, the universe could have come into existence at a specific time, but out of a material that is eternal and will eternally exist in a certain sense. So that quantum field, we have to prove its existence. If we prove its existence, it still doesn't prove the multiverse. It proves there is a potential for the multiverse to exist because this field existed at this finite time in the past for an infinite earlier time. And then it's kind of, some people call it like hubris to think we're the only universe, in the same way that thinking we're the only planet or whatever would be. That's more of like a philosophical kind of rational argument. But in reality, there's good reason, if you buy that the universe cannot stop producing these universes. Once one universe forms, that's necessary and sufficient to prove that a multiverse is possible. But of course, you can't prove that a multiverse exists. You could only disprove that it didn't exist. You could say that that we have discovered that there is no possible way for a multiverse to exist because we can't see this particular type of quantum field, or we observed there are alternate models for how the Big Bang occurred, including another universe collapsing on the Tuesday before our universe began. That collapsing universe has nothing, there would be no multiverse in that case. You'd have another problem, where did that universe come from? But that might be also infinite in a certain sense. Yeah, it's pretty wow. Let's see. Jeffrey Love, thank you very much. Thank you, it's my pleasure. Any other questions from the audience? Well, I appreciate being with you guys on this dark, late winter night, and I hope to come back here again, maybe with some other news in the future. Thank you guys. Thank you very much.
Are we still on? I can say something?
Oh, yeah.
Yeah. Okay, so Dr. Keating, I wanted to thank you and also your wife, Sarah, for coming out here this weekend. I know you're going to be here in town, or our little town, for a little bit, and so I hope you really enjoy the time that you're here as well. And so with that, I'll say good night. And everyone who's here in our live audience can come up and talk with Dr. Keating, buy books, whatever you wish. Okay, good night. Bye-bye. I'm not quite sure how